As you learned in the short video, we can use stable isotopes in the ice to determine temperature, and bubbles of trapped air to determine the composition of the atmosphere. Let's first explore how we determine temperature. As snow and ice accumulates in polar glaciers, a paleo record accumulates. The water in the snow and in the ice contains oxygen and hydrogen. Both oxygen and hydrogen have isotopes, and the ratio of these isotopes tells us about global temperature. Earlier, we investigated how radioactive isotopes can be used to estimate the ages of archives. Now we will consider how stable isotope ratios can provide information about changing climate. The most commonly used element in paleoclimate research is oxygen. There are 3 stable isotopes of oxygen: O16, O17, and O18. O16 is the lightest and most common. O18 is heavier. The ratio of O18 to O16 in water is affected by temperature. We've already looked at this plot. Recall that isotopes are shown in horizontal lines and that stable isotopes are shown in the black boxes. The 3 stable oxygen isotopes are circled in red. Note all 3 have 8 protons, but because they have different numbers of neutrons, their atomic mass varies. Oxygen 16 is the lightest, oxygen 18 is the heaviest. The 4 main points that you need to understand about oxygen isotope records in ice cores are shown here. To denote the ratio of O18 to O16, we use delta O18. That's shown in black here. This value is the ratio of oxygen 18 to oxygen 16, standardized to SMO. SMO is the standard mean oceanic water. Delta O18 in water is largely controlled by temperature and the distance the water vapor has traveled. I'll explain this more in a minute. Oxygen 18 in ice cores can provide an estimate of global temperature, whereas delta O18 in marine sediments tells us about the amount of water locked up in ice sheets. How are oxygen isotopes in ice cores related to global temperature? Recall, at the equator, large amounts of water are evaporated. Water molecules containing the light oxygen, O16, are slightly more easily evaporated than molecules containing heavy oxygen, O18. As the water vapor moves north, it cools, and condensation of water results. Water containing heavier oxygen isotopes, O18, condenses faster than water containing lighter oxygen, O16. Therefore, as water vapor moves northward, it becomes more and more depleted in O18 and more enriched in O16, causing delta O18 to become very negative. The processes at work are enhanced with colder temperatures, so that waters reaching the poles when temperatures are cold are even more depleted in O18 and enriched in O16. Water depleted in O18 that falls at the poles is incorporated in glacial ice. Because the water vapor has been affected by temperature throughout its journey from the equator to the poles, delta O18 in ice cores provides a record of global temperature. At the same time, marine waters are becoming more and more enriched in O18, and as O16-rich water is trapped in ice, this enrichment is increased. Therefore, during cold periods on Earth, ice at the poles is very depleted in O18, whereas ocean waters are very enriched in O18. Much data has been collected to determine the specific relationship between delta O18 and temperature. This is one example from Svalbard in the Arctic. This plot shows that delta O18, shown on the y-axis, is dependent on temperature. shown on the x-axis. The colder it is, the more negative delta O18 becomes. Because of this relationship, we can use delta O18 in ancient ice to tell us what global temperatures were in the past. When you watched the thin ice video, you saw scientists collecting samples in snow pits. This was to determine the relationship between delta O18 in the snow and measured temperature. This plot shows time on the x-axis from 1990 to 1994 and temperature on the left y-axis, delta O18 on the right y-axis. What do you observe? There's a strong correlation between delta O18 and temperatures, right? There's also a clear seasonal variation, with winter delta O18 values being more negative than those in summer. Using the relationships between delta O18 and temperature, determined using calibrations such as this, scientists have calculated temperatures from ice cores going back 800,000 years. This plot shows the temperature reconstruction from an Antarctica core going back 800,000 years. How could you validate this record? What patterns do you observe? What could be driving these patterns? The observed fluctuations on the last slide are the result of the Earth going from glacial to interglacial cycles. But what causes ice ages? We now know that ice ages are driven by changes in the Earth's orbit around the Sun, which results in variations in the amount of solar radiation received by the Earth. This theory was originally put forth by Milankovitch in the 1920s. Milankovitch was arrested in Serbia at the start of World War I. The quote here is from Milankovitch describing his thoughts on the day he was imprisoned. He accomplished many important scientific works on Earth and other planets' climates while in prison. Milankovich's theory describes that there are three variations of the Earth's orbit around the Sun: eccentricity, obliquity, and the precession of the equinoxes. Let's take a look at each one in turn. This NASA website provides an excellent explanation of the Milankovitch theory, as well as some very nice visualizations. This is a great overview of what we're going to talk about next. Eccentricity describes the changes in the shape of the Earth's orbit around the Sun, from circular to elliptical, and back to circular again. This cycle occurs every approximately 100,000 years. Obliquity refers to changes in the tilt of the Earth. The axial tilt varies from 22.1 to 24.5 degrees and back to 22.1 degrees every 41,000 years. Changes in obliquity mainly amplify or suppress seasonal differences. The greater the axial tilt, the greater the seasonality. The last is the precession of the equinoxes around the Earth's orbit. Like a top, the Earth wobbles as it rotates. One axis wobble occurs every 26,000 years. Watch this video of wooden tops to better understand the Earth's wobble. This slide illustrates what the wobble looks like. When the Earth's orbit is circular, the precession of equinoxes has no effect. However, when it is elliptical, the Earth is sometimes closer to the Sun, referred to as perihelion, and sometimes farther from the Sun, referred to as aphelion. Because the Earth wobbles, sometimes the northern hemisphere is pointing towards the Sun during aphelion, as in the upper panel, meaning cooler summers and more moderate winters. Other times, the northern hemisphere is pointing towards the Sun during perihelion, as is the case in the lower panel, meaning warmer summers and colder winters.